So I covered the reaction earlier, reaction 1, correct? You finished that? All right, let's take a look at the reaction 2 more detail. But actually, what we could do for reaction 1 is we could just do a little bit of stoichiometry for that to see what the yield was. And when you do this, you're going to use your amounts to calculate. What we're going to do is we're going to calculate the theoretical yield. But the first calculation is just to show that how much excess, and so let's just do a calculation to show, how much excess, if any, oxalic acid is used. OXAC is the abbreviation for oxalic acid. Yeah, normally we do these things in the lab notebook, so everything in the lab notebook doesn't have to be in a neat, presentable form like the formal report does. And so what you do is you take all the data from the lab notebook and then you formulate the formal lab write-up. And so you should have the calculations. Now calculations don't require experimental data, so typically what people do is all the observations they write on the front page, and on the back side they'll do the calculations or whatnot in pencil. Is fine for that. But you can use, we have plenty of pages, so you don't have to worry about running out of pages. So you could do it anywhere, but you shouldn't skip pages. Did you guys see my post on the lab notebook? Okay, just some general guidelines there. All right, so the reaction was we had dichromate. What was the stoichiometry of the reaction? How many dichromates? Just one. Okay, plus what? H plus? In the balance, I want the balanced redox reaction, so plus 8H plus 3 oxalic acids. Now the oxalic acid is also going to supply H plus, but something has to take it from the oxalic acid, whereas this H plus, actually this H plus is, where was this? Did we add acid to this? Other acid? No, so this has to also come from the oxalic acid. All right, anything else? Okay, and this is going to yield what? 6 CO2 plus what?
2 chromium 3 plus 7 water.
And so in this mixture we just had it depends. We just had the dichromate and the oxalic acid, and it depends on where the source of this H plus is. The source could be water, but we're going to need a little bit more than that. And so probably what we're going to have to do here is we're going to have to add some additional oxalic acid to supply this. Does that make sense? But if we were just to do straight stoichiometry and have an external source of H plus, how much oxalic acid minimum? Because we could get this from other acids. The only problem is other acids are going to leave some residual contaminants that we would have to get rid of. But it's possible we could get rid of that just by washing our crystals. So if we just did straight stoichiometry, how many grams of oxalic acid did the procedure say to use? 10 grams of oxalic acid. So obviously use your number here.
Oxalic acid or the dichromate?
Oh, dichromate. How many grams of dichromate? 4 grams? Is that right? 3.6 grams. Okay, 3.6 grams was the ideal mass. here. 3.6 grams. And that would require a minimum of what in terms of oxalic acid? So we have 3.6 grams, but this is potassium, correct? Dichromate. Was it anhydrous or was it a hydrate? Was it monohydrate? It was anhydrous, okay. All right, then what we're going to do is we're going to figure out how many moles that is. And so we'll need the molar mass of potassium dichromate. The molar mass of potassium dichromate, I don't want to calculate right now. I'll just look it up. K2Cr2O7. And so molar mass is 294.185. I wish. We'll just use that as is, 294.185, because I don't know if this 5 was rounded up from 4, so I'm just going to leave it. Normally I go 2 decimal places, which is enough. So this is for the potassium dichromate. So grams will cancel, and that leaves us with moles of potassium dichromate. But in this equation we have dichromate, but we can see for every mole of dichromate required, we would need 1 mole of potassium dichromate. And then we're going to need a minimum of 3 moles of oxalic acid for every 1 mole of dichromate. And then we didn't use pure oxalic acid, we used the hydrate. And the hydrate was the monohydrate, as I recall. Is that right?
Yeah.
Dot H2O. For every mole of oxalic acid that I need, I'll need 1 mole of the monohydrate. And then, again, I'm just going to look up the molar mass of oxalic acid monohydrate. The pub chem also should have it 108.05 grams per mole. But this is it the monohydrate? Do you see that? When I look at the formula here, it shows C2H4O5. So oxalic acid is H2C2O4, and then, yeah, then it works out. That would be the monohydrate, 108.05. I'm not going to write everything. This is just make sure all the units cancel out. So the moles cancel out, dichromate, potassium cancels out, this cancels, this cancels. And that leaves us with, that leaves us with grams of oxalic acid monohydrate. So let's figure out what the minimum amount we should have used is. 3.96. We are allowed we should use about 4.0 grams. How many grams did you use? More like 10 grams. But, you know, this is a minimum. It depends on our source of H+. If all our H+ has to come from the oxalic acid, then we're going to need an additional 4 moles of oxalic acid, because 4 moles of oxalic acid would give us 8 H's, correct? But they'd have to be plucked off. And so if the source of this H+ here is from the oxalic acid, then altogether we'd need 7 moles. You know, and so let's write that here. If the source of the 8H+ is H2C2O4, then we'll want an additional plus 4 moles. So what that means is that this ratio here is going to change to 7 moles of oxalic acid per 1 mole of dichromate. Oops, is that right? No, this ratio here. Well, no, this is the correct ratio, sorry. All right, so if we recalculate this, then how much? So what I do is I'll just do 7 times 7 divided by 3 times 7 divided by 3, my previous answer. And so if we recalculated, then I should use 9.25 grams of oxalic acid dihydrate, or monohydrate, sorry. So I should use 9.3 grams, you know, if we have 2 sig figs. You're going to have 3 sig figs because it says to weigh 3.6 grams, but our balances weigh 2 decimal places. So if it says weigh 9.6, you'd weigh, I mean, if you hit it right on, you'd weigh 9.60. You know, you weigh to the full precision of the balance. And so we should have 3 sig figs here, you know, in our calculations. So this came out to 9.255. This was, I forgot. So we'd need about 9.26 grams, you know, of the oxac.H2O. We used 10 grams, so we should be okay, correct? The limiting reagent is going to be the dichromate. Now, we're not going to calculate the yield of chromium-3 plus here, because we're going to take this chromium-3 that forms here and immediately react it. And so there's no reason to calculate how many grams or how many moles of chromium-3 I form. So we're going to go here for reaction 2. We're taking the chromium-3 that just formed. Now what I want to do is when I do a sequence of reactions, I'm going to keep it the same. So I formed 2 chromium-3s here. So what I'm going to do is I'm going to start off with 2 chromium-3s here. And then I'm going to add potassium oxalate. Was it potassium oxalate?
Yeah.
Was it a hydrate or was it anhydrous? Anhydrous, okay. So we're going to add the potassium oxalate here. Really, the potassiums are spectators. And so this reaction here, just ignoring the potassiums because those aren't going to do anything, is we're going to have our two chromates, and each chromate is going to need 3 oxalates. The oxalate's a bidentate ligand, so we'll need 6 oxalates altogether. And so this is going to form 2 of the trioxalato chromate 3 ions. So how much are we going to need? So how much potassium oxalate will we need? So we have 2 choices. One, we could start off with how much chromium 3 plus we formed. That's probably that could be the best, but in theory, what I'm going to say is 100% we're going to react it with. So we'll just add on to this reaction here. Or maybe we'll just do that calculation. Okay, yeah, maybe we'll just do that here. What I'm saying is here, rather than figuring out how much oxalic acid, we'll just figure out how much product will form. There are different ways we could do that. You know, I'll do it the long way. There's shortcut ways we could do this. And so let's see, amount of chromium 3 formed from reaction 1. So here we're going to start off with 3.6 grams of the dichromate, potassium dichromate.
For the complex, is it 2 minus or 3 minus?
3 minus. Thanks. And then we just use the molar mass we got earlier, 294.185. grams per mole. It gives me moles of potassium dichromate. Here the mole ratio is going to be a bit different. But what I'll do is I'll just say, I'm going to do this. I'm going to say that we're going to get 1 mole of dichromate ions. Oops, no, I don't want to do that, sorry. Well, I guess I'll just do the same thing. For every 1 mole of potassium dichromate. And then I'm going to get 2 moles of chromium 3 ions for every 1 mole of dichromate. And then I'm going to get the mass of chromium. Just get it off here. 51 point. We'll just go 52.00. It should be good enough. So we'll have 52.00 grams per mole for the chromium. And so how many grams of chromium 3 ion should I have gotten? 3.6 divided by 294.185 times 2 times 52. 1.272 grams of chromium 3 ion. So that's what we're going to start off with here. we're going to calculate how much oxalate do I need for this. But I'll leave it at this. So this is to be continued here, because we're analyzing the reaction from before. All right, let's take a look at the lab next. Did you have a chance to read through the lab? Yeah. So let me take a look. I guess I must have closed it. Pull up the All right. Normally, when we do these labs, you would do these pre-lab questions. And when I was, let me tell you, when I was at UCLA, we typically started with a pre-lab quiz. So I'd have to prepare for the pre-lab. Usually, I don't normally give a pre-lab quiz, but sometimes I might. But I'll let you know in advance. All right, what Le Chatelier's principle is. Le Chatelier's principle is if there's an equilibrium established, let's say like this. This is called a dynamic equilibrium. It's a dynamic equilibrium because nothing appears to be changing, but it's dynamic because it's always changing. That is, if we look at this, this is the formation of diamine silver 1 ion. But when we're at equilibrium, the concentrations stop changing, but the reaction never ceases. And so we have forward reaction here and reverse reaction, and it's just struck up some balance. This balance lies very far to the right. These complexes are quite stable. And so this is heavily favored to the product. But what we can do is we can shift this. We can shift the balance. Normally this is heavily favored to the product, but if we start removing ammonia, so if you start taking out the ammonia, then it's going to shift the balance, because what's going to happen is this is going to go reverse to compensate for the removal of the ammonia. Well, how can you remove ammonia? Well, there are different ways we can remove ammonia. One, we could just let it evaporate off the surface. So if we don't cap the bottle, we'll have ammonia, degas out of solution. And as the ammonia leaves the solution, because ammonia is normally gas, so it's a very soluble gas, so it wants to stay in water, but some of these ammonias are going to have very high energies that can vaporize off the surface. Or two, we can take an advantage of a chemical property of ammonia. What's a chemical property of ammonia that you know? Well, for metathesis, it hydrolyzes water, and ammonia can be used to precipitate out hydroxide, metal cations as hydroxide salts precipitates. That's a metathesis. For acid base, you know that ammonia, or at least Bronsted acid base, you know that ammonia is base. Is a weak base or a strong base? Normally we think of ammonia as a pretty weak base. You know, things that would be a strong base would be hydroxide. What else? Sulfide. Amide. Amide kind of looks like ammonia, but it's NH2 minus. It's a very strong base. Amide is actually the conjugate base of ammonia when ammonia acts as an acid. Methide, oxide. Those are the strong bases. So it's a weak base. That's a weak Bronsted base, but ammonia turns out to be a strong Lewis base. This is a Lewis acid-base reaction here, and ammonia is an excellent Lewis base, and so this is why the products are so heavily favored here. Ammonia is great at attacking silver ions and other metal cations as well. Here we didn't precipitate out the hydroxide. Normally when we have ammonia and water, ammonia hydrolyzes water, right, to form a little bit of hydroxide. So we'd expect to form some silver hydroxide here. And we do. Initially silver hydroxide does form, but if you keep adding ammonia to this, what happens is the ammonia just starts attacking the silver ions directly to form this amine complex, and this amine complex is quite stable. And so if you were to do this, you would probably see a two-phase reaction. The initial phase is the metathesis, which happens, let's say, quick. And then, and it also depends on the concentration of the ammonia. But the higher the concentration of ammonia, the more this is favored, the amine complex here. Ammonia is an excellent Lewis base for these types of things. But how can we take it out? Well, one way we can take out ammonia is we can maybe precipitate out some other cation instead of silver ion. But you know, that leads to a lot of complex mixtures and precipitates and whatnot. An easier way to take out ammonia is by taking advantage of its Bronsted base properties. All we have to do is add a Bronsted acid. Now the Bronsted acid cannot precipitate out with silver ions. Otherwise, we could take out the silver ions as well. You know, that would shift this. But let's say we don't want to take out the silver ions. Then we need a Bronsted acid that will not precipitate out with silver ions. Can you tell me a Bronsted acid that won't precipitate out with silver ions? Like, for example, if I use hydrochloric acid, is that good? The hydrochloric acid, the problem with using hydrochloric acid is chloride and silver like each other and they'll precipitate. And so yes, we'll remove the ammonia by attacking it with H+. If we attack ammonia with H+, we're going to form ammonium ions. Ammonium ions don't participate in this reaction here. But the silver ions would also precipitate, leaving a cloudy mixture here. So give me a strong acid that won't precipitate out with silver ions. Nitric acid. Nitric acid's good. The problem with nitric acid is ammonia. You know, nitric acid is one of the properties of nitric acid is a strong what? The redox properties. One of the redox properties of nitric acid is a strong oxidizer. Ammonia is electron rich. You know, you have to be careful. Like there's a household safety rule. The household safety rule is do not mix ammonia with bleach. Ammonia is a good reducer. Bleach is a good oxidizer. You're going to create probably oxides of nitrogen. Oxides of nitrogen are toxic, and you might have potentially a violent reaction. And so we don't mix ammonia and bleach. And so you know, nitric acid, maybe you want to be careful with nitric acid because nitric acid might oxidize the ammonia because they're at opposite ends of the nitrogen redox spectrum. And so what do I mean by opposite ends of the nitrogen redox spectrum? Oops, actually I was going to go to this page here. Nitrogen's oxidation state varies from what to what? Yeah. It ranges from +5 to -3. On the +5 end is nitrate ion. That has nitrogen in the +5 oxidation state. On the -3 end, we have ammonia. And so ammonia we consider electron rich. Nitrate we consider electron poor. Here. And so there's both of these are nitrogen. So one nitrogen is extremely rich, the other is extremely poor, and they're both nitrogen. What do you think is going to happen? This is going to be a reaction, right? Is nitrogen versus nitrogen, who wins? Who wins? There should be a tie, shouldn't it? Because they're both nitrogen. And so here's a situation where they aren't tie. And so if there's a tug of war, nitrogen versus nitrogen, which nitrogen is going to win? No, there's going to be a reaction here. Can you see it? Yeah, there should be a reaction here. So anyway, a lot of thinking goes into this, and eventually what they do is they just tell you, okay, what are we going to use? They're going to add acid to this. When they add acid, it's going to take out the ammonia. If you take out the ammonia, this thing is going to go backwards because we're losing ammonia. The ammonia is keeping this going forward. And if we add hydrochloric acid, it's also going to precipitate out the silver ions. We're not using nitric acid. We could use nitric acid, but they probably don't want to generate any toxic gases in this particular case. So we're going to use hydrochloric acid, which is also going to precipitate out this silver chloride. They give us a caution because we're using 15 molar ammonia, so we're using quite concentrated ammonia. And the quite concentrated ammonia gives a powerful odor, and so if you get it under your nose, you're going to definitely smell it, and it's going to kind of be a shock because it'll clear out your nasal passages immediately. You know, it's not like household ammonia you can smell, but 15 molar ammonia is really to do something, like in smelling salts. And so be careful with that. Even though it's a weak base at this concentration, you got to be careful. I guess we're also going to acidify with nitric acid, so we have to be careful with nitric acid as well. But anyway, we're just going to follow these steps. So some of the cautions here are things like silver ions. Silver ions are, as far as metathesis goes, they react with chloride, bromides, and iodides. As far as acid-base goes, they're Lewis acids. They'll react to form complexes like this. They aren't Bronsted acids, but they're Lewis acids. As far as redox goes, silver ions are what? Well, actually not weak. They're pretty moderate. You have to use the conjugate relationship because silver is a stable metal. If silver is a stable metal, its conjugate, silver ion, is going to be a moderately strong oxidizer. So silver is a stable reducer, meaning silver ion is a good oxidizer. You can tell if silver ion gets on you because it easily oxidizes your skin. So when silver oxidizes your skin, what forms? Black. It stains your skin black, and you know what the black is? The black is tiny crystals of silver metal. You know, as the tiny crystals of silver metal grow bigger and bigger, then they start to have that silver color and luster. But it stains your skin black, and you don't want to get it in your eyes. Did I tell you I had a student, this is in Chem 4, and the student had black splotches all over their hands, and they told me they were washing their hands. I forgot for how long it was, for a very long time, like 30 minutes or 45 minutes. And they said they had a job interview right after lab. And they didn't want to go to the job interview with all these black, but unfortunately, you can't do anything. You got to wait until, you shed that skin. But you'll want to watch out. So silver nitrate, silver chloride, all these are, and silver is also a heavy metal, so you have to watch out for heavy metal poisoning as well. But anyway, we're going to do different things. So if I want to shift this to the right, I could add more iodide or I could add more silver. You know, that'll shift it to the right. If I want to shift this to the left, then I got to remove some of these. And so we're just going to play with shifting these to the right and the left, and there has to be some kind of observable change. And so the observable change you'll just look for. Okay, so you want to watch out for nitric acid. It says avoid contact with nitric acid. It's a pretty strong oxidizer. You'll know if you get nitric acid on your skin, because do you know what nitric acid stains your skin? What color it does stain your skin? It stains your skin with, it stains your skin yellow. So if you have black and yellow splotches, then you had silver ions and nitric acid. And I think it was the nitric acid is going to obviously oxidize your tissue and form NO. And the NO, which is nitrosyl, is a decent, actually pretty good Lewis base, and it could attack your, I think, heme and form a nitrosyl complex. And the nitrosyl complex is yellow, as I recall. It's been a while since I looked at it, but that was it. So watch out for nitric acid. You know, we call it an oxidizing acid to differentiate it. The HCl, which is not as powerful of an oxidizer, you still have to watch out for this because we're using 12 molar. 12 molar, you can really smell it. You know, it's quite corrosive because HCl is normally gas. And at this concentration, it's coming off, it's vaporizing off the surface of the liquid. The nitric acid, what are we using here? 6 molar. 6 molar they call dilute, but 6 molar is still pretty concentrated. 12 molar they call concentrated hydrochloric acid. So the concentrated hydrochloric acid back there, it causes burns to tissue, so watch out for that. Usually you can tell if you spilled hydrochloric acid just by having a slight burn on there. What other things do we have to worry about? Ammonia. Okay. So this one, we can control this. This goes from light blue to dark blue. So we can shift this to more dark blue by adding more ammonia. We can shift it to light blue by getting rid of the ammonia, attacking it with acid. And so that's the basic point here. And these are just rough observations. You know, just look at what happens. You don't have to be careful about the amounts or anything. You could use the spot plate. Do you guys have the spot plate? Spot plate, you could just use drops of reactants and just do it in one of the little dishes on the spot. And I think it's pretty straightforward. The last one, though, you know, all the balances, the product to reactant ratio is fixed, except the last one, I think we changed the temperature. When we change the temperature, it changes the K value. K is dependent on temperature, just like delta G is dependent on temperature. And so if you change the temperature, you change the driving force. You change the driving force, it's going to change the ratio, product to reactant ratio. Okay. Whereas if we don't change the temperature and we just add more, or we remove some, the ratio doesn't change. It's just got screwed up. That's all. Is that clear enough? All right, so let's go ahead and work on this lab for today. This lab you can work with a partner if you want, or you can work solo. It's up to you. The report for this lab is going to be different than the last one. The last lab we're going to write a formal scientific report. This one we're just going to answer some questions regarding the lab. So they're just asking for the colors, you know. So this is pretty straightforward. This is light blue. However, the complex was a dark blue. What happened after HCl addition?
It was back to light blue.
It went back to light blue. So after HCl addition, it changed to light blue, let's say. How about NiCl2? Yeah.
Light sea foam.
What was it again? Green?
Like a light bluish green.
Blue-green, light blue, whatever. The colors are subjective, so anything close is fine, you know. The amine complex, this is the hexamine nickel 2,
Came like blue purple.
blue-purple, all right. And then after HCl addition,
Back to light blue green.
okay, light. Okay, explain the effects of ammonia and HCl on CuSO4 solution in terms of Le Chatelier's principle. Consider them the following equilibria. Did I not copy that? All right, the equilibria they're talking about is this. Just write it here. And that would be a copper 2 ion plus 4 ammonia yields the tetramine copper complex. So we could explain this, you know, in a formal report, we would explain this in a paragraph or two. You know. For this, we could explain it just pictorially. So explain the effects of adding ammonia. So let's say over here we'll add ammonia. So what we're going to do is we're going to be adding additional ammonia here. And that means we're going to have a greater population of reactants, and that greater population of reactants can make more product. And so we call this a shift. So additional ammonia is going to shift it to the right because of the additional reactant. Does that make sense? So we'll have additional collisions, it's going to shift right. And so the effect is we have a right shift. In Le Chatelier's, we talk about right shift or left shift. And so this shifts it to the right because we're going to have more product formed in this case. On the other hand, if we add HCl, so let me write down here. We'll take this same equilibrium, and so it's going to have the same, you know, ratio. That is the balance to product and reactants, but it could have different concentrations. This is at equilibrium, so I should draw 2 arrows. 2 arrows is to signify we have a situation where we've reached this state of dynamic equilibrium. 4, 2 plus. And so what the HCl is going to do is the HCl will attack the ammonia and just remove it. And so we could either do this as net ionic. In net ionic, HCl has H plus that likes ammonia, and that's going to convert the ammonia to ammonium. So what we're going to see is we're going to see a decrease in population of the reactants. If we see a decrease in population and the population of the product stays the same, then there's going to be a shift. This is going to result in a shift left, right? Because the population of product is too much to sustain with a decrease in the population of reactants. And so what we say is it shifts the equilibrium to the left. So shift left. This is just qualitative. We can do this quantitatively by calculation too, which we're going to do in chapter 15. So again, they ask us for the colors, and they're asking us to account for the changes. So we just write out the equilibrium with the cobalt. What was the equilibrium for the cobalt that we're looking at? Okay. What do we have? Cobalt H2O6. So this is the aqua complex. 2 plus or 3 plus?
2 plus 4 CO minus.
So we form the cobaltate ion. So we go from hexa-aqua cobalt 2 to tetrachlorido cobaltate 2. And then we'll have 6 waters. Now this is often done. Actually, do I need the parentheses here around chlorine? No, I don't. Let me get rid of those. I don't need the parentheses. Did the coordination number all of a sudden change? So we went from a coordination number of 6 to coordination number of 2. The answer is it actually didn't. There are 2 aquas there. And aqua sometimes isn't written. So if I see the hexa aqua, you know, that's the same thing as just saying cobalt 2 plus aqueous. Sometimes the aquas are strongly bonded, and sometimes the aquas are very loosely bonded. And so oftentimes this is the same thing here. So the effect of adding, account for the changes observed. So after the addition of HCl, well, if we add HCl, we're adding chloride. And so that's going to impact this. So if we add chloride, we are increasing the population reactants. If we increase the population of reactants, although you know the cobalt's not increasing, but having more chloride is going to result in more reaction nonetheless. So some of the cobalts that didn't react before are now reacting now. And that's going to shift it to the right. So we see a right shift here. Now, what if we add water? What does that do? If we add water, we're reducing the concentration. Now, if we reduce the concentration of the product and the reactants equally, then there's no impact. But the situation here is this. This is a liquid, so that's pure. So reduction in concentration is going to have a greater impact on the reactants because we're reducing the concentration of this and this. It's kind of weird to think about, but it's not even because water's pure, and so we don't really think about that. And so this has like a, you know, an uneven impact on this. So actually, let's go with a different color here. So K for this is going to equal the concentration of the complex. Sometimes we get rid of the brackets here, but otherwise it kind of looks funny. So this is the concentration of the complex here, the product, raised to the first power, divided by the concentration of this aqua complex. Divided by the concentration of chloride. Now the concentration of chloride is raised to the fourth power. And so when we look at the concentration here, it's going to have a larger impact on the reactants than the products. There's a concentration dependence. So when you added water, which color did it shift towards? Did it shift towards the aqua or the chloro complex? It shifts towards the aqua. Now, this is tricky because you're diluting it anyway, you know, and so it's hard to tell what the effect is. But here, adding water dilutes everything, but it's going to dilute the reactants with a larger impact here than the products. We're going to look at this more in chapter 15. So hopefully we'll better explain it then. But add water, we shift left. Equilibria involving sparingly soluble salts. Now, what were you supposed to put in here on line 10? You have to read the procedure and see what they were asking for. What were they asking for on line 10?
I didn't write it down.
All right, let me see what they're asking for here on line 10. So I see 12. 11 and 10. Here we go. To half a milliliter, 10 drops of 0.1 molar sodium carbonate in a clean, large test tube, add 10 drops of 0.01 molar silver nitrate. Record your observations on the report sheet. So what did you observe?
In an opaque white solution.
All right, was it a white solution or was it a precipitate? Okay, so what we say we could say here is formed a white PPT. This is what we'd expect because the reaction here is 2 silvers plus the carbonate should precipitate out silver carbonate. Okay, the next observation they want is this. Cautiously add 6 molar nitric acid dropwise to the test tube until you observe a change in appearance of the contents of the test tube 11. Save the contents for the next step. So you added silver nitrate to that precipitate you just formed. What happened? Oops. Shoot, did that? Here, I have to. All right, so what happened here?
Precipitate fully dissolved.
Precipitate dissolved. Did any gas form?
I didn't notice.
Okay, what was the color of the solution that formed? Okay, so CCS. Precipitate dissolved. I'm just going to write an arrow to CCS. I was expecting some gas to form because we'd have silver carbonate solid plus 2H plus from the nitric acid. This is going to yield 2 silver plus CO2 gas plus H2O liquid. And so I was expecting some effervescence from the CO2 gas, but the solid should dissolve. We have a driving force here. Now you might think, okay, we're getting rid of one precipitate and not replacing it with any precipitate, but all we need is one driving force here, and so we're okay. What is CCS? Clear colorless solution. It's a common abbreviation, so it looks like water. consider the following equilibria. Okay, the first equilibrium is just a precipitation reaction. You know, we expect that. There's a driving force for both of these. Here. Now, they want us to explain it in terms of Le Chatelier's principle. So in terms of Le Chatelier's, we do it something like this. We would go 2 silver ions plus a carbonate. This is going to go to silver carbonate, so solid. In terms of Le Chatelier's principle, what we see is that, okay, you know, none of these precipitates are 100% insoluble. So what we're going to have is we're going to have an equilibrium between the precipitate and its saturated solution. And so this would be the saturated solution. Now when we add H+, the H+ is going to attack the carbonate. And so we have 2H plus a carbonate in this case. I was attacking the silver carbonate solid, but we can attack the carbonate that is in equilibrium with the silver carbonate solid by adding H+. So 2H pluses plus a carbonate, this is going to yield CO2 gas plus 2H2O liquids. So as we reduce the carbonate concentration, what is going to happen is we don't have the normal equilibrium. We don't have the normal up and down. And so we're going to get a shift to the, this whole thing should shift. Left shift. This is in terms of Le Chatelier's principle. So what do they want us to do for 12 here? I guess that was for 12. I think I was supposed to write it down here, but it's all right. 13. Did the precipitated silver chloride dissolve? Well, let me make sure 12 and 13 I'm on the right one. To the solution saved from above, add 0.1 molar HCl dropwise until you observe a change in the appearance of the contents of the test tube. Record your observations on your report sheet. 12. To the solution saved from above. Okay. So in 12 here, did you add HCl to a solution or did you add it to a precipitate? To a solution? Okay. Well, actually, let's go ahead and look at this first. So we have Ag plus Cl minus. This is going to yield a precipitate of AgCl solid. The more chloride we add to this, the more it's going to shift it. And so let's look at the first part of this here. Working? Okay, there we go. Plus chloride is going to result in a shift to the right. Now this is the equilibrium. This is the equilibrium between the precipitate and its saturated solution. So we have a dynamic equilibrium, which is going to be heavily favored towards precipitate here. But adding chloride is going to shift this to the right. However, adding ammonia shifts this to the left. Because if we add ammonia to this, ammonia is an excellent Lewis base for silver ions. And so what we end up with is the silver ions will react with 2 ammonia to form the diamine silver ion. silver 1 ion. And so this removes the ammonia. I mean, this doesn't remove, this removes silver. If I remove silver, then this should shift left. If I add enough ammonia, I can completely redissolve the precipitate. Because if I just keep adding more and more ammonia, I'm removing more and more of this, and then more silver chloride will dissolve. And eventually, all of it will dissolve if I add enough. So did the precipitated silver chloride dissolve? Okay, we could say yes with excess ammonia. So, did it? I don't know, I'm just asking. Yes, with excess ammonia, we have a left shift. Ultimately ending in all the precipitate dissolving. It can and did dissolve. So this is kind of how we write it up. When we do calculations, we're not going to write it up like this. This is very qualitative. What effect did the addition of HNO3 have on the contents of the test tube? Well, HNO3 is going to screw up this second equilibrium here. And so if I look at this second equilibrium, this is also an equilibrium as well. And so looking at the second equilibrium, the two ammonias are tagging the silver ions. We're moving it. Adding HNO3 is, well, it's going to attack the base. In this case, the base is ammonia. So essentially, it's H+. Nitrate we want as a spectator. So we have to be careful of the concentration we use here, because we don't want it to start oxidizing the ammonia and creating toxic gas. And so essentially, we're going to have 2 of the ammonias plus 2 H pluses. And we just want this acid-base reaction. We don't want a redox reaction to occur. And so we'll have to keep an eye on the concentration of that. So this is going to result in a shift left. If this shifts left, then we're going to generate more silver ion. If we generate more silver ion, we're going to reprecipitate out silver chloride, because it's going to impact the first equilibrium. So the end result is it increases the silver ion concentration, which is going to result in a precipitation, AgCl. From the first equilibrium, it's going to shift it to the right. What effect did the addition of ammonia? Addition of ammonia is going to, if we increase the concentration of ammonia, that's going to decrease the concentration of silver ions, which is going to result in a shift left, which ends up dissolving the silver chloride. Explain the effect of the addition of Ki. Did you add Ki to the ammonia or just Ki to the silver? Well, silver likes iodide ions. Did we have a competition? So in other words, did you add the potassium iodide to the solution up here or to a totally different solution?
To the solution of the
Okay. Then what we have is we have a competition. So silver plus iodide yields silver iodide. And silver plus chloride yields silver chloride. So chloride can attack silver ions or iodide can attack silver ions. Which one won? Both are trying to form precipitates. Which one won? How you can tell which one is the winner is by the color. Silver iodide has a different color than silver chloride. What was the color of silver iodide?
Is it like the cloudy?
This is like cloudy. This is cloudy white.
Yeah.
Silver iodide's not white. What color is silver iodide?
Feel like a light blue.
It's not blue.
Is it the what?
I'm sorry?
Is it the chloride?
Are we adding the potassium iodide to the silver? It was the wrong thing. I was not supposed to open that. Shoot. You see what color? Yellow. So was this precipitate more white or more yellow? More white?
It was weird. It was like cloudy on top, then a strip of clear, and then.
Did you
all
mix
the-
it?
Yeah.
Okay.
Or like I tapped it. Swirled.
So everybody got white? Pretty much? All right. So it looks like silver chloride's more favorable than silver iodide based on observations. Now this one we do via Le Chatelet's, but it's a little bit wrong. So we need this one, the cobalt. And so what's happening with the cobalt here? So that's probably talked about at the beginning here in the discussion section. What happened with it?
When we heated it,
Yeah,
it just kind of got darker.
darker. And so the way we do that is we take a look. What was the reaction here? What was inside the test tube?
I believe it was the cobalt chloride.
Okay. And was there HCl in there?
No, it's just
Okay, just that. Let's see, where was the temperature? So 1 milliliter cobalt 2 chloride in a small test tube, and place the test tube in boiling water without spilling. Compare the color of the cool cobalt solution to the hot cobalt solution. And so basically what we want to do is we want to know what's the reaction there with the temperature, but we don't have to. And so you said the hot was dark
Yeah.
and this was light. And what was the color? Red?
Yeah.
And as you heated it up, it turned dark red, correct? And so what we have is we have to figure out what the light red is. What is the cobalt complex that's light red here? And then we added heat or energy, and we formed the dark red. And so heating this will add energy and shift it to the right. The opposite, cooling this, will remove energy and shift it to the left. And so this is Le Chatelier's here. But in reality, what happens with temperature is K is a function of temperature. And so K changes. With temp. Okay? So that's kind of it, what we're doing. We should figure out what the identity of these are, but I'm sorry? Is it reaction endothermic or exothermic? Endothermic, yeah. The rule here is that increasing temperature favors the endothermic direction, and so like melting ice. Melting ice is endothermic. Increasing temperature favors melting ice. Freezing water. Freezing water is exothermic. You have a freezer that removes heat, and dumps it behind the freezer. And so freezing water is exothermic, and exothermic's favored at low temperature. All right. Any questions on this?
Just for the future labs, should we be doing the 3 lab questions?
It's a good idea.
Should we do it in our notebook or just?
In the notebook. Yeah.
Will you do lab quizzes?
Lab quizzes, if people come totally unprepared, then we may have a quiz. Otherwise, there won't be any lab quizzes. Uh-huh.
So is the light red the hydrated cobalt? And the dark red is the separated?
Well, that's a good question. What is the equilibrium you're talking? What is the light red? What is the dark red? And so you're saying the light red is the hydrated cobalt? Is that what we observed earlier? And so if we take a look at the observations from earlier with the chloro complex here, what were the colors here of the aqua versus the chloro complex? I didn't write them down.
I want to say it was like clear red in the beginning with the hydrated, and then with the hydrochloric acid it became darker. It was darker than the red.
So the But there was no HCl in this, correct? This is just straight
Either way.
cobalt 2 chloride. One of the things we might do is do something similar to this, but we don't have the excess chloride here we need. And so we need some additional, they should give us some additional information to determine what the species are. Could be that the dark red, you know, if you increase the temperature, for some reason the chloroligand's getting in there. And so increase in temperature might disfavor the aqua ligand and replace it with the chloroligand. That could be it. But I'd like to see a little bit more than that. And so it could break this apart and then chloroids can attack it. But what we'll just play it safe and just go ahead and write, you know, there's something there. This is pretty well known. So if this were a regular we could look it up. Here. This is with a chloride, CF2. We could do a little bit of research, so maybe you could research it and then see. That would be good. All right, other questions? I guess, are we, what time do we end? 12:55? All right, what you can do is you can just go ahead and complete the report, you know, if you want to turn that in. Or take a look at your crystals, check the progress. Or you could work on the other lab, you know, start doing some stuff for the other lab. In fact, I could talk about the other lab. Do you want me to talk about the other lab?
Like the synthesis or the next level?
Synthesis lab. Actually, what is the next lab we're doing? Today's Wednesday, it'll be Monday.
So for the synthesis, what you wanted us to write out some reactions before like the procedure and whatnot. Do we have to write out reactions for this lab?
What do you mean? Write out the reactions for this lab?
With the reactions that occur?
I just wrote them up on there on the sheet.
Yeah.
So just copy those
And then
down.
put them in the
Right, right, right.
Next week it says we're in the computer lab.
Next week we're in the computer lab. All right.
Yeah. The same.
Reactions, analyzing those. Were you still working on the lab, Mitchell? You just need to clean up? All right. I'll leave some time at the end. All right, this is how many grams of chromium 3 plus. And so the first thing is, let's calculate how much potassium oxalate is required to react with 1.272 grams of chromium 3 plus. And so amount of potassium oxalate required to react with 1.272 grams of chromium 3 plus. How many grams of potassium oxalate did you add? Or how many were you supposed to add? 4.2. Okay, so let's go ahead and calculate this. 1.272 grams of chromium 3 plus, and then the molar mass was 52.00 used per mole. It gives us moles of chromium 3 plus. And then I know I need 3 moles of oxalated ions for every 1 mole of chromium 3. This is going to be the trioxalato complex here. And then I need 1 mole of potassium oxalate for every 1 mole of oxalate, 1-to-1. Now, remind me, was the potassium oxalate anhydrous or was that a hydrate? Anhydrous. Okay, then I need the molar mass for potassium oxalate. And so I'm just going to look that up. K2C2O4. There is an unhydrated form. K2C2O4. 166.22. And so I have 166.22 grams per mole for potassium oxalate. And so grams, moles, and that leaves me with grams of potassium oxalate. So let's go ahead and calculate how many grams this is. 1.272 divided by 52 times 3 times 166.22. 12.197 grams. How many grams did you add again?
Around
4.2 grams. Okay, either this either I did a mistake in my calculation, so I double check this. Let's see. So 3.6 divided by 294.185 times 2 times 52. 1.2726 divided by 52 times 3 times 166.22. Yeah, 12.2 grams. All right. So this is going to get kind of complicated here because we added excess oxalic acid. Now, oxalic acid and potassium oxalate can do the same thing. And so there's going to be a competition here with chromium. So when I think about oxalate, Oxalate's a dibasic base. It's a base. And when I think about oxalic acid, that's a diprotic acid. But when I'm talking about base and acid, this isn't in the context of Bronsted. And so what can happen here is this. What can happen here is that oxalic acid and oxalate, even though one's an acid, the other's a base, they both can act as Lewis bases. And so this is going to be a Lewis base, which this can attack here. And so this oxalic acid has a choice. It could either bond to the hydrogen here or it could bond to the chromium. It picks chromium. And the H's leave. And so we end up with the same thing being that the only difference is we had to knock off the H pluses, but knocking off the hydrogens is not difficult if it's reactive enough. And so we end up with plus 2 H pluses here. So doing the calculation is going to be a headache because we did have excess oxalic acid. How much excess oxalic acid do we have? Not that much because we needed, what, 9? But the H plus, you know, that was assuming that, if we go back to this earlier reaction, that was assuming the oxalate actually reacted. If we look back at this original reaction here, the oxalates don't have to react. It's just the H plus we needed here. And so this is really kind of weird because what happens is the excess oxalate and excess oxalic acid from reaction 1 can be used in reaction 2. Does that make sense? And so we actually do have enough oxalate to do the reaction. And that's because this H plus, if this H plus is coming from oxalic acid, then there's still oxalate around, unreacted. This oxalate, however, reacts to form CO2. But 8 out of 11 don't react. And those 8 out of 11 can still maintain. All right. And so it appears that there's some kind of discrepancy here, but there isn't. And so what I'm going to do here is, in this particular reaction, for reaction 2, I'm going to write it like this. I'm going to write plus 6 C2O4 2 minuses plus actually, let me erase this. Or H2C2O4. H2C2O4 will do the same thing. We just have to knock off the hydrogens for it to react. And so we could use either reactant. We could use the potassium oxalate. Potassium oxalate is going to give us oxalate directly. Or we could use the oxalic acid. Oxalic acid, if we knock off the hydrogens, will give us oxalate. And we had excess oxalic acid. We just didn't add enough potassium oxalate to do the whole thing. This is keeping things a little bit cleaner in terms of the product mixture, but it's keeping things messier in terms of the stoichiometry. So the note here is both oxalic acid and potassium oxalate can react in reaction 2. And I did have excess oxalic acid, although the H pluses need to be used for the reaction 1. And so I did have excess oxalate. So 4 grams were added.
Yeah.
4 grams appears to be not enough. But it turns out it is enough. We can show this by calculation. Otherwise, we're going to have chromium-3, residual chromium-3. And it's possible we do, but it's all right. At least it's not dichromate. Now, reaction 3 was taking 3 potassium ions and the trioxalato chromate 3 ion and 3 waters. This is all soluble. However, if we increase the ethanol content of this mixture, we can get this to precipitate out. So this is our original precipitation. And then what we did is a recrystallization. In the recrystallization, we're just trying to reverse this by taking our solid. This is our solid we isolated by filtration. And dissolve it in water. This aqueous solution here, it's a strong electrolyte, so it's going to break apart. Probably should have broken apart completely earlier. In fact, let's go ahead and just write it as the solution here. Okay, and then repeat. We add the ethanol, and hopefully this will precipitate out. But our goal here is to generate large crystals. And so we'll just let our crystals grow more. Our goal is to grow large crystals with high purity. Secondarily, it would be good to get a good yield, but we might not get a good yield, so let's go ahead and calculate the theoretical yield. And I told you the stoichiometry is kind of messy because of the oxalic acid and potassium oxalate. And so for multi-step synthesis like this is what we do. We combine all the equations. And so when we combine all equations, we're going to end up with a net equation. And the net equation is going to look like this, where we'll have our dichromate, and this is going to yield 2. So for every dichromate, this is our LR, limiting reagent, we will get 2 of the complex. And that is, the reason we're doing it like this is because we want to make sure that all the chromium, we don't lose any of it. And so all the chromium that was originally here ends up here. So we had 2 chromiums over here. We better have 2 chromiums over here. So that's why I multiplied by 2 here. And so that way we didn't lose any. So the mole ratio is 2 moles of product for every mole of dichromate. This gives 2 moles of product, that is precipitate, for every 1 mole of dichromate. We add it. And so what I'm going to do is I'm not even going to balance all these. I'm just following what's happening with the chromium. Since chromium was my limiting reagent, I'm going to assume I'm not missing much of it. And so I have 3.6 grams of potassium dichromate, and that was with a molar mass of 294.185. So 1 mole of this was 284.195, I think, grams. Make sure. 294.185, sorry. 294.185. And then we have 2 moles of the K3 CrOx 3.3H2O for every 1 mole of the dichromate. Now we need the molar mass for the complex. Let's see if I could find the molar mass of this complex. So I'm just going to type in K3 Cr. Now oxalate is C2O4, so I'm going to type in C2O4 rather than use the abbreviation 3. .433. If this is going to compute it for me, I'm going to try to make the hydrate 3H2O. Let me see if it'll compute it. No. That didn't work, unfortunately. But this was kind of convenient. So I have 433.348, and then I'm going to add 3 waters. So water is, what is water? 18.02. 3 times 18.02 plus 433.348. Or just calculate it myself. 487.41. This is for the second compound here. Probably should label it so I don't get confused. Times 2 divided divided by 294.185 times 3.6. So in theory, we should have gotten 11.929 grams of product. This is my theoretical yield. And so after we dry our crystals, we're going to weigh them and see how close we come out to this yield. We probably lost a whole bunch, but that's all right. All right, I'm going to stop here. Were there any questions on this? Okay, I just wanted to talk about some of the reactions and calculations. Uh-huh.
I was looking at the actual lab sheet that you posted, and it looks like there's like a lot more. Is this all we're doing? Or are we gonna?
That's all we're doing. Yeah, we aren't doing any of the other syntheses.
I was just wondering how much space I needed to have about it.
Just for this type of stuff. That's it.
Did this go in the lab notebook? Or did this go in the
It
lab
doesn't
notebook?
have to go in the lab notebook. You know, it's not mandatory, but normally people put it in the lab notebook because they just keep everything in the same place. You know. Again, like I said, you could write on the back side if you don't have room. You could put this type of stuff. This type of stuff can be done in pencil too, because you can always generate the calculations whenever you need to. You know, versus the observations of the experiment, you'd have to repeat the experiment to do that. Okay. All right, if there are no questions, then we'll just wrap it up for today. That's it. Thanks.
Do you have a test book?
Yeah, I have your tests.